Um, sorry.
No, go ahead.
Did you put up a practice exam 3?
Yes, they're all up now. It's in the orientation module. Here, I'll show you. If you go to the modules, practice exams,
Okay. I'll grab it.
they're all there.
Modules.
So Mark, Elizabeth, thank you for having your cameras on. Do appreciate it. And Corina. Hello there. Okay, now I gotta turn this back on.
Forward to seeing the aquarium tomorrow.
I
And
know.
And your mic is on?
Oh, sorry, I meant.
That's okay. I just wanted you to know. All right. So I am going to be using this for other classes as a recording. So if you want to hide or change your name or whatever.
Sorry.
And your mic is on?
Yeah, I just realized that. 1 second.
All right, let's get started. All right, welcome everybody. This took a good hour and a half with the other class. I want to take my time with these and answer any questions that you might have. So hopefully you have the practice exam 3 and can follow along with me. Let's start here, number of farms. A random sample of the number of farms in thousands in various states follows. Estimate the mean number of farms per state with a 95% confidence. And this is sort of a big clue here. We need this anyway. And yeah, okay. So first thing that we need to do is load this information into our calculator. Let me clear mine. All right, so I'll give you a minute to load these in. And I'll give it another minute, let you guys finish up. Andrea, your microphone is on.
I'm sorry.
That's okay. You're welcome to keep it on. I just want to let you know. Okay, so this is going to be a Z interval. And so I'm going to go to stat tests Z interval, which is down here, line number 7. And this is 31. And we are using raw data. And our confidence level is 0.95. And it says round final answers to 1 decimal point. Getting this here. I know the interface of my graphing calculator looks different than yours, but it should be displaying pretty much all the same stuff. Any questions there? All right, I'm just going to keep going. If you need me to stop or explain something, you just need to speak up, please. Water temperature. If the variance of the water temperature in a lake is 26 degrees, now I want to be clear, this is a squared is 26. How many days should the researcher, oh, I'm sorry, this should be sigma squared. How many days should the researcher select to measure the temperature to estimate the true mean within 3 degrees with a 95% confidence? Okay, so I want to be clear. This implies that sigma is the square root of 26. Remember, variance is the standard deviation squared. They're also giving us E, which is the 3 degrees. And the formula we're going to use is here. Now they're giving us that alpha is 0.05, which means alpha over 2 is half that. And z sub 0.025 is inverse norm 1 minus 0.025. Now we need to be careful here. It says round the intermediate calculations to 2 decimal places. So when I get this inverse norm, I'm only going to go to 2 decimal places. This is about 1.96. And that's actually what I'm going to use in the formula. Remember, we always round up. All right, let's keep going.
So if it's 11.1, you still go to 12 days?
We always round up.
Okay, just wanted to make
Because we're looking for a minimum value, and we never want to not quite have enough. We always want to make sure that we have at least enough. All right, number 3, state gasoline taxes. A random sample of state gasoline taxes in cents is shown here for 11 states. Round sample statistics and final answers to at least 2 decimal places. Use the data to estimate the true population mean gasoline tax with 98% confidence. Assume the variables distributed. Okay, So as we're looking at this, I noticed that they don't tell us anything about the population standard deviation. So this means this is going to be a t interval. So let's put the data into our list.
Professor,
Yeah,
um, we're doing a t-interval test on this problem, and I think the first problem was a z-test.
a z
Problem
interval.
number 2, z-interval. Problem
Uh-huh.
number 2, was that a particular type of test?
That was not a test. That was that was them wanting to know the minimum number of the sample that we would need to accomplish a certain confidence level.
Is there a name for that formula?
Not that I'm aware of. It's
Okay,
on the it's on the list though.
Okay, thank
Yeah,
you.
it's on that sheet.
Gotcha. Thank you.
You're welcome. I've never heard it having a name, so I'm sure someone has named it at some point.
Can we all just agree that it's now called the Asia formula?
Agreed. Agreed.
Okay,
You got
cool. We named a formula after me. Accomplished. Thank you.
it. And they'll know it's you because the way you spell it too.
Thank you.
All right. There, it's official.
I can die happy. I've done a thing.
That's awesome. Actually, while I'm waiting for you guys to finish putting that in, real quick, my wife actually has a theorem that's named after her that they still use at Cal State Long Beach. I'm not making that up. That's a real thing. It's called
No
Saito's
way.
last theorem. Yep.
What's it called?
Saito's last theorem. It's not going to be like on the internet or anything like that. This is just a local thing.
That's so cool.
Yeah, I agree. There's a whole history behind how it got named, and anyway, it's kind of fun. All right, we are going to do a t interval, and I'm going to use data from list 1. And what is the confidence level? 98, that's right, 0.98. And I don't think it says where to round it off. It does not, so we'll just go to 1 decimal point again. 0.7. And does the interval contain 44.7 cents? The answer is no. The national average of 44.7 cents is not contained in the interval. Yours, of course, will be a drop-down menu. Any questions there? All right, we are moving on. Hospital noise levels. For a sample of 4 operating rooms taken in a hospital study, the mean noise level was 38.4 decibels. And the standard deviation was 10.5. Find the 90% confidence interval with for the true mean of the noise levels. Okay, now you'll note that we, again, know nothing about the standard deviation of the population. The standard deviation that they give us is based on the 4 samples. So we have, so this is going to be a t interval again. And we have x bar is 38.4. Sample standard deviation is 10.5. And our C level is at 0.9. All right, here we go. T-interval again. So done. There. X bar 38.4. 10.5. N is, what was it, 4? 4. And our sea level, 0.9. There we have it. Not too bad. We just gotta know what test to run, really. The ones that get messy are the ones with the standard deviation, because we got to do the chi-squared table and the whole deal. Manual transmission automobiles. In a recent years, 6% of cars sold had a manual transmission. A random sample of college students who own cars revealed the following. 123 out of 123 cars, 27 had manual transmission. Estimate the proportion of college students who drive cars with a manual transmission with a 99-degree confidence. So what we have is we have that X is 27, N is 123, and our sea level. Whatcha? All right, our sea level is 0.99. And we are going to be running a 1 prop C interval. One prop Z interval. Now, be careful, it's not one prop Z test. It's one prop Z interval. That means that it's my A way down at the bottom there. So it says around the final answer to 3 decimal places. There we are.
Hi, professors, me again. Sorry, guys. I'm just really trying to get this down because this is the hard unit for me. Is there, and I think this question came up already in class, but is there a differentiating factor between when we're using Z interval versus, what's the other option? I'm sorry.
A T interval.
I understand
So
the
the
difference between Z and T, because I know if we're missing the population standard deviation, that's the distinction between
Right.
those two, correct?
Right, that's right.
Okay, but when we're running the test, the respective like Z tests or the Z interval tests,
So
is
you're
there a
mixing up
word
some of the
that
vocabulary
tells
here.
us or something in the data that
So if they're looking for a confidence interval, then it's going to end with the word interval or INT. If they actually want to run an actual hypothesis test, then it's going to end in the word test.
Okay.
You can see there's a lot of them. And at the top are the tests, and below that are the intervals. And then even below that, there's some more tests, which we will learn in chapter 10 and 11.
Okay.
Yeah, so right now they're just doing confidence intervals.
Gotcha.
Yep. And keep
Thank
asking. That's okay. Even if it's the same question again, it's totally fine. A federal report indicated that 20% of children under age 6 live in poverty in New York, an increase over previous years. How large a sample is needed to estimate the true proportion of children under age 6, living in poverty in New York within 1% with 90% confidence. Okay. So the formula that we're going to be using for this one is here. Again, this is on that sheet. And they are giving us, so far, they're telling us that E is the 1%. P hat is the 20%. Come on. Which makes Q hat the 80%. Remember, it's the complement of P hat. Now they're also giving us alpha, which is 10%. That's from the confidence level, the C level. Alpha over 2 is going to be 5%. And Z sub 0.05 is inverse norm 1 minus 0.05. Now, I couldn't get the answer to match the answer in the key because they didn't tell us how many places to round off that inverse norm. So I'm going to round it off to 3 decimal places. So I'm going to say that this is 1.645. And that's what I'm going to use in the formula. This should give us our count.
Where did you get the Z from again? I haven't done this one since.
Inverse norm?
Yeah, the Z. Where did? I mean, from the description, where did you get the 0.05?
So it's Z sub alpha over 2, and alpha over 2 is 0.05.
Okay, so the 1% in New York within 1%.
That's the E. That's the denominator.
Okay, yeah. So where in the question did you get 0.05?
Okay, so if we look here, this means that alpha is 10% or 0.1. And if I take 0.1 and divide it by 2, that's my 0.05.
Okay, so it's like a two-tail.
Sort of like a two-tail. That doesn't really apply to this type of a problem. This is just part of the formula.
Okay.
So let's see what we have. 1.645 squared times 0.2 times 0.8 divided by 0.01 squared. And this is 4,330. So this is the minimum number needed. And we know it's this type because it's asking how large a sample is needed. The other one that we did, which was here, it's asking a similar type question. It's saying, how many days do we need? So these are some of the cues. Any other questions before I move on? Okay, this one is messy. So a study of life expectancy showed that a random sample of 6 states, that is my N, which means my degrees of freedom is 5, had a standard deviation of 1.3 deaths. per year. Find a 90% confidence intervals of the variance and the standard deviation. Assume the variable is normally distributed. Okay. So the formula that we're going to be using is going to be here. This is for the variance. And once I get the number for the variance, I'll just take the square root of that to get the standard deviation version. So since it's a 90% confidence interval, that means alpha is 0.1, which means that 5% are going to go in each of these. Of course, right in the middle is 0.9. And from this point over to here, it's going to be 0.9 plus 0.05, which is 0.95. And area to the right here is just going to be 0.05. Let me stop there and let you get caught up for a second. Okay, so we have to use our table. Remember, degrees of freedom is going to be 5 in this case. So degrees of freedom is 5. And for 0.95 and 0.05. So we are here, we are here. Everybody with me how I'm finding these numbers? Okay, 1.145. And for this one, I've already forgotten, it is 11.071. 11.071. All right, so this is going to be 5 times 1.3 squared divided by 11.071. And 5 times 1.3 squared over 1.145. Times 1.3 squared divided by 11.071. They want us to round up to 1 decimal point, so that's going to be 0.8. And right below it, I'm going to go ahead and take the square root of this number since I already have it up here. So square root of the previous answer. That's going to be 0.9. Now let's do the other side. 5 times 1.3 squared divided by 1.145. So this is going to be 7.4. I'm going to take the square root of that. It's going to give me 2.7. So there are my answers. Any questions I can help with?
Yeah, why did you do the square root?
Because if you notice on the left there where the answers are, one of them is sigma squared and the other one is just sigma. So to get rid of the squared, you just take the square root of each.
No, I don't understand.
Do you remember back in algebra?
Nope.
I guess you do.
I took algebra 30 years ago.
I understand, but the way that you get this answer is you take the square root of both sides.
Okay.
So that's what we're doing here. To get sigma by itself, I'm going to do the square root of each one. Yeah, I confused that.
How did you do the square root again on the calculator?
It's above the squared button. It's if you go in the first column,
Mhm.
the second, then alpha, then math, then x, then -1, then x squared. In a
Mhm.
little above it, it says the square root on that same button. So you have to
Okay.
hit the second button first and then the x squared button.
Okay.
Now, you could have started out with, I would not recommend it. You could have started out with this one. This is the same formula. And then when you got each of those answers, then you would just square that and then you get the one above it. So you could do it either way. Anybody else? It just, oh, no, never mind. All right, let's move on. Keep the questions coming. The mean SAT score in mathematics is 541. Standard deviation of these scores is 33. A special preparation course claims that the mean SAT score, mu, of its graduates is greater than 541. So let's write that down. So mu is 541, and their claim is that they can get it higher. An independent researcher tests this by taking a random sample of 70 students, so there's my N, who completed the course. The mean SAT score in the mathematics for the sample was 544. At the 10% significance level, can we conclude that the population means SAT score for the graduates of the course is greater than that? And then this is the key sentence here. Assume that the population standard deviation of the scores of the course is also 33. So what they're telling us essentially is that we have the population standard deviation. This is going to be a z-test. Degrees of freedom do not apply in this case. This is a greater than case, so this is going to be a right tail. Let me stop there for a second. And to find the critical value, I need to do inverse norm. Not 0.01, it's 0.1. All right. They do want to know the critical value. And again, we're going to be running a z-test for this one. Mu in this case is 541. 541. Sigma is 33. X bar is 544. And N is 70. And this is a greater than. So our test statistic is 0.761. And I want to point out that the p-value is 0.223, which is definitely bigger than our alpha. And I'd like to make it clear that our test statistic is definitely not in the critical region, or the rejection region, I think ALEKS calls it. So we're going to fail to reject.
Can I see your calculator again?
Uh-huh. One sec. Any questions I can help with? I see things in the chat. Yeah, I hear you. Sorry, I'm reading the chat. I'm just getting caught up. Yeah, I agree, Leighton, for Kemi. Just focus on the practice test. Do it as many times as you have time for.
Okay.
Yeah, don't get too discouraged. We're only about a week. We're almost done. All right. Is that enough time with the calculator?
Yeah.
Okay. So we're going to fail to reject the null hypothesis. What that means is we're sticking with the null hypothesis. We think that that the mean is still 541. So can we support the claim that it's greater? No. No, we cannot. Any questions here? Yeah, luckily there's almost no actual math in this. It's mostly the calculator doing all the heavy lifting for you. Rachel recently switched her primary doctor to one specializing in caring for elderly patients. On her new doctor's website, it says that the mean systolic blood pressure among elderly females is 120 milliliters of mercury. Rachel believes that the value is actually higher. So they're saying that the mean is 120, and they think that it's more than 120. Rachel thinks that it's more than 120. She bases her belief on a recently reported study of 20 randomly selected elderly female adults, elderly female, pardon me. So that's N is 20. the sample mean systolic blood pressure was, so X bar is 134. And the sample standard deviation was 25. And I see nothing here talking about the population standard deviation, which means we're going to be running a t-test. Now, there is a standard deviation, but it's the sample standard deviation. And I know Cami isn't the only one that's nervous about the test coming up. So everybody just go down swinging, just if you're going to go down. So hopefully no one will go down. But if you do, just do the best that you can. That way, if you have to retake the class, you get the most out of this one, so it'll carry over to the next one. But I'm hoping everybody passes. That's my hope.
That is so nice of you, but you're gonna have to keep some of these problems off of the test. That one like 2 problems ago, the one that was really messy.
Oh, yeah.
I used
That-
my
that one.
newly formed statistic skills, and I was like, what are the odds that I will still pass this test if I get one of those?
No,
I
just-
use stats to figure out my odds when I saw that one. I was like, wait a minute.
No, you'll be fine. Just like I said, just keep focusing on the practice exam.
Yeah,
I designed the regular exams very much like those.
yeah. Thank you, Professor.
Also in the homework, when you get to those types of problems, just do like 10 of them, just back to back to back to back, just nonstop.
I agree. I do seem to like hammer my way through this through repetition. I don't like it, but when it clicks, it clicks. But the best thing for me to do is to like go all the way through, like do all the homework from the chapter and do the test because everything like is fresh. I
Right.
get nervous about the exams because I have to recall stuff that I may not have retained. So sometimes understanding it is like doable. Retaining it is where I get a little nervous, but we'll see how it goes. Like you said, go down swinging.
Yeah, I agree.
Well, my problem is that I'm having some problems getting things right, some things right, because I still can't understand it at all. So I'm getting part of the questions wrong, and I don't know why. And I even had tutoring today, and I'm still like, I went back and started showing homework again. I'm like, why am I getting, now I'm getting opposite stuff wrong.
Yeah.
So yeah, it's confusing, and I don't know how to keep hammering it out, and I'm exhausted.
I know. All right, so let's find the critical value here. Inverse t. Remember, the degrees of freedom are 1 less than the n. Yeah, I'm supposed to be in a meeting in 15 minutes on Zoom. That's not going to happen.
We don't round that up to 1730 in ALEKS.
So if we want to go to 3 decimal places, then we need the 729, and then we look just to the right of the 9. If that's a 5 or higher, then we go up. But because it's a 1, we keep it.
Oh, that
Yeah.
might be why I'm getting some things wrong. So you look at the last number, and then if the number after that is 5 or higher, we round up.
That's right.
Okay.
All right, so let's run a t-test. And here we have 120. X bar is 134. Standard deviation is 25, is it really? 25. And n is 20. And this is a greater than. All right, so our test statistic is 2.504. And I want to point out that our p-value, actually, let's move that over here. Zero point zero one one. And that is definitely less than our 0.05. And at the same time, my test statistic is in the critical region. So we are going to reject the null hypothesis. Meaning we don't think that it's 120, we think that now it's more than 120. So can we, that the mean systolic blood pressure is greater than 120? Yes, we're on board. Any questions? All right, let's keep moving. One bit of good news is it says that it's 10 out of 18. There's actually only 17 now. Number 17, we get to cross out, and I took it off of your practice test, and it's definitely not on the test. According to a report done by S and J Power, the mean lifetime of light bulbs it manufactures is 46 months. A researcher for a consumer advocate group tests this by selecting 25 bulbs at random. For the bulbs in the sample, the mean lifetimes is 50 months. It is known that the population standard deviation of the lifetimes is 9 months. So let's, whoa, what happened? How did I do that? Okay, so let's start here. Mu is 46. And this is a not equal to. So this is going to be a two-tail. We have n is 25. And the key sentence here is population standard deviation lifetimes is 9 months. So we know sigma. We know X bar is 50. And did they give us an alpha? Alpha is 0.05. So because we know sigma, or the population standard deviation, we are going to be using a z-test. Yep. It's going to have two tails. And because alpha is 0.05, this is going to be half of that. The other half is going to be here.
What module? Is this from module 8?
Yes,
Do you know what section?
8.1.
Okay.
Degrees of freedom do not apply here. So we have our critical values. Do we need our critical values? Not as much for this one. So we're going to run a z-test here. And this is 46. And 50. And is 25. And this is a not equal to. So this is Z is about 2.222 with a p-value of 0.026. All right, and let's compare that to, this is definitely smaller than our alpha. And I can see that my test statistic is in the critical region. 2.2 is more than 1.96. Our conclusion is that we're going to reject the null hypothesis. Meaning we think that it does differ. We don't think that it's 46 months.
Can you tell us which problems, like from here on out, are from which section? That would help me with my homework a lot.
Okay.
It's a little confusing for me right now. I have so much stuff going on in my head with the numbers. I'm just like getting confused.
Do you want me to go back?
No, that's fine. I understand where the other stuff came from. It's just from chapter 7.
Here, I'll tell you, I'll do them, all of them from chapter 8 so far.
Okay.
Okay, so this is section 8.1. This one is section 8.2. This is section 8.1. And, oh, we haven't done that one yet. Okay. If I forget, just remind me. All right, I'm gonna move on if that's okay. I'll take the thumbs up. All right. On their website, a property management company states that the mean monthly rent for apartments on the east side of town is $675. A researcher for a consumer advocacy group believes that due to the construction of newer apartment complexes in neighboring towns, the mean monthly rent on the east side is now lower. Okay, so let's start with that. A random sample of 15 monthly rents for apartments on the east side has a mean of 667 with a standard deviation of 15. Assume that current monthly rents on the east side are approximately normally distributed based on this. There's our alpha. Okay, they tell us nothing about the population standard deviation. That makes this a t-test, which means it's section 8.2. Degrees of freedom are going to be 14.
Is there, I mean, I know it's probably not going to ask, it'll let us know if we need a degree of freedom. If it's a t-test, it'll ask that, correct? Or chi?
Yeah, chi-squared or t is going to
Okay.
have a degrees of freedom.
Okay.
And our alpha is 10%. So let's run a t-test. Oh no, let's find our inverse t. 0.1 degrees of freedom is 14. All right, let us run a t-test. So this is 675, 675. X bar is 667. Standard deviation is 15. And n is also 15. And this is a less than case. So negative 2.066. P-value 0.029. Let's see. Our p-value is definitely less than 10%. And I can clearly see that my test statistic is in the rejection region. Reject the null hypothesis. Meaning we don't think that the mean is 675 anymore, we think it's less. So can we conclude that it's less? Yes. All right. Once we figure out what test it is, it's really kind of the same thing over and over again. All right. Anybody need more time there? I see something in the chat. Oh, you got it, Leighton. With John. Yeah. All right, we are moving on to number 12. A marriage counselor has traditionally seen that the proportion P of all married couples for whom her communication program can prevent divorce is 75%. After making some recent changes, the marriage counselor now claims that her program can prevent divorce in more than 75%. So here is mu is 0. I'm sorry, not mu. This is P now. And thinks that it's more than 75% now. In a random sample of, so here we have N is 205, X is 170, stayed together. Based on the samples, are enough support to support the marriage counselor's claim at the 5% significance level. Proportions are always Z, always normally distributed. And because this is greater than, this is going to be a right tail test. All right, this is going to be a one proportion z-test. This is section. Oh, I'm wrong on the labeling. Sorry, let's go back. This is 8.2. Sorry, problem 8, section 8.2. Problem 9.3. Problem 10, this is 8.2. This is section 8.3. And this one is 8.4. Sorry about that. Elizabeth, you're getting mauled by your dog.
He's very happy to do math today.
Oh
All
my
right.
God, he's so big. My dog's 13 pounds.
My
Oh
dog's
my God.
under 7 pounds.
Oh, what, really?
Yeah.
I didn't know you had such a little dog. Yeah, I thought my dog was small. How much does he weigh, Elizabeth?
He weighs 80 pounds.
Oh, he looks very hairy then.
Yeah. And he's very fluffy. He has like a double layered coat. I have two chihuahuas that are like 7 and 14 pounds.
That's hilarious.
They complement each other very well.
All right. As much as I would love to talk about dogs, got me a job to do to get you guys through this test. All right. Now I can see right away that this is way less than 5%. And I'm clearly, my test statistic is clearly over here. Yeah. So we don't think that the mean, or with her new program, the mean success rate is not 75%, but it's something bigger than 75%. So we are going to say yes. We think that the proportion has gone up. Good for that counselor and good for her clients. Any questions here I can help with? All right, let's keep going. Jonathan, just so you know, your mic is on. Which I don't mind if it's on, as long as you don't mind that it's on. Based on their records, a hospital claims that the proportion P of full-term babies born weigh over 7 pounds is 35%. Pediatrician who works with several hospitals in the community would like to verify the hospital's claim and investigates. In a random sample of 240, so let's start writing some of this down. So first of all, mu is 0.35. And the claim is that they don't know if it's 35. They're challenging it. They're not saying it's more or less. They're just saying they don't think it's 35. And we have N is 240. X is 104. And I think that's all that we're going to need. This is
We don't put P here instead of mu?
P. Thank you.
Phew.
I've been doing this all day. So thank you for catching me. And this is going to be a Z. Let's draw it out. This is a two-tail. And we're going to run once again. This is section 4, 8.4. And we're going to run a 2-prop z-test. 1-prop z-test. Come on, Kevin. So 1-prop z-test. And this is a not equal to. And this is 2.707. And the p-value, even though it doesn't ask for it here, and that is definitely less than our alpha. Our critical values are -2.576 and 2.576. And not only is our p-value less than our alpha, our test statistic is definitely in is definitely in barely the rejection region. 2.7 versus the 2.5. Either way, we are going to reject the null hypothesis. So we don't think that it's 35%. We think it's something other than 35%. How are we doing? All right. If I remember it, this next one's going to be. Yep. Here we are. This is a standard deviation. So we're going to be using a chi-squared. All right, buckle up. Here we go. Records from previous years for an electronics company show that it rejected a mean of 1.8 circuit boards per batch produced with a standard deviation of 0.4. I see. The factory manager suspects that because the company now uses a new molding process, the standard deviation has changed. So She tests a random sample of 14 batches, which means our degrees of freedom is 13. Produced using new process and finds that the mean number of circuit boards rejected is 2 per batch. We don't care about that, but what we do need is the sample standard deviation. If we assume that the circuit boards rejected per batch using this new process are approximately normally distributed, is there sufficient evidence to conclude at the 1% level that the manager is correct? Okay. Let's start here. Uh-oh. Oh, what a cute dog. Thank you, Leighton. Okay, we need to find our critical values. We're going to have to use the table. And just to point out, this here in the middle is here. This is going to be our chi-squared left. This would be our chi-squared right. And the area to the right is 0.99 plus 0.005, which is 0.995. And this one here, 0.005. So 0.995 and 0.005 with the degrees of freedom of 13. Okay, so first off, our degrees of freedom are here, and we're here, we're here, and here. .565. And 29.819. 29.819. 29.819. Are you getting a little more comfortable with the table, hopefully?
Yes. I had a question about the other table, the T distribution. We only use that for.
You only
when
use that
the-
if you only use that if you have a super old TI-83 that doesn't have inverse T in it.
Oh.
But
so
your
I don't-
calculator has inverse T.
Oh, okay, so I don't need that table.
Right.
Okay, so it's just chi-squared.
The only one that you're going to need for this class is chi-squared.
Got it.
All right, so we have all that. This is definitely going to be a chi-squared distribution. All right, we have the two critical values. Now we need the test statistic. I also want to find the p-value. And because it's two-tail, and I'm doing this manually, I'm only going to get half the p-value.
Can you explain a little better about when you do I know you're going to times this by 2 to get the actual p-value, right?
Correct.
And then when you do the right tail and the left tail, how does that differ when you when you do the equation on the calculator? I get a little confused on that.
Ask me again. I didn't fully understand what you meant.
Well, because this is a two-tail, we do the 0 and then we do I guess you're entering
The test
the
statistic.
test statistic and then the degree of freedom. How would you
Correct.
do it if it's a right tail and a left tail or a left tail?
Right. So I know because the sample standard deviation is less than the population standard deviation, meaning the 0.22 is smaller than the 0.4,
Mm-hmm.
then it's going to be the left tail.
So I'm just wondering how you'd enter it on the CDF. So you'd put that at the bottom or the left in the calculator.
In the calculator, because I'm starting at 0, it's going to automatically be the left one.
Okay.
Because we're going to here, which is the 3.9325.
I just get confused on how to do the p-value when it's a left tail or a right tail with the CDF. Getting the p-value.
Right. So remember, it's always from the left to the right when you're
Okay.
doing a CDF. And so the left is the 0. You can see the 0 in the graph.
Yes.
And it's going up to the 3.9325.
Okay. Okay.
So it's going to find that area. And then I just need to, whatever that area is, I just need to double that and that'll get me the right one.
Okay. Does the degree of freedom always go on the right, even with the left tail or right tail?
Yeah, yes.
Okay.
So chi-squared CDF 0, 3.9325, 13. So this is, again, the half of the p-value. And then the p-value is going to double that, so times 2. And I can see that that is larger than my alpha. And my test statistic is not in the rejection region. Cami, just so you know, your mic is on. So we are going to fail to reject. The null hypothesis. Which means we think that sigma is still 0.4. So do we think that the process differs from the 0.4? No, we don't. This is section 8.5. Now this one didn't ask for the p-value, but the test question might. So it's good that you know how to do that. Even when you're doing the practice, try to come up with the p-value. Now, if this was a left or a right tail only, then we would only we wouldn't double it. That would just be our p-value. Any questions? This is a lot to absorb. All right, we only have a few more to go. According to past research, cholesterol levels of adult males are approximately normally distributed with a mean of 233 and a standard deviation of 21.6. So that is our Some researchers specializing in healthcare claim that because healthier foods have become more expensive, the standard deviation sigma of cholesterol levels of adult males is now less than that. Research take a random sample of 16 adult males and measure their cholesterol levels. The people in the sample have a mean cholesterol level, we don't care, and a standard deviation of 13.7. So N is 16. So degrees of freedom is 15. And we have capital S is 13.7. Is there enough evidence to conclude at the 5% level that the standard deviation cholesterol levels of adult males is now less than 21.6? All right, let's do this. And to be clear, if 5% is there, this means 95% is here. So we'll need to find the critical value. So our degrees of freedom is 15, and area to the right is 0.95. So we are now here, 15.95. So our critical value is here at 7.261. This is definitely a chi-square. Degrees of freedom is 15. I don't think I filled that in the previous one. This is also section 8.5. So we're going to find the test statistic as well as the p-value. So let's start with the test statistic. And unfortunately, that is definitely in the critical region. So to find the p-value, I messed something up, hang on.
So if it was a right tail, then we would put the test statistic first and then put 99999.
Sorry, That's exactly right.
And then the degree of freedom.
Mhm.
Okay, that's what I was wondering earlier.
And you are correct.
The ALEKS calculator for the p-value is super easy. It's just a p parentheses x squared greater than, and then you put the test value in the degree of freedom.
All right, test statistic 6 chi-squared is about 6.034. P-value 0.021, which is less than our alpha. So because we're in the rejection region and at the same time our p-value is less than our alpha, then we are going to reject the null hypothesis. Which means we think that the standard deviation is less than 21.6. And so we are affirming, yes. Any questions I can help? All right, let's keep going. All right. We are now to section 9.1, I want to say. 9.2. 9.2. All right, two popular brands of tires for tractor trailers are the Puma and the Eternal. LaShonda is a buyer for a major shipping company and wants to determine if there's any difference between the two brands of tire in the mean distance driven on them before they need to be replaced. So we'll start here. They want to know if there's any difference. LaShonda tests a random sample of 13 tires from Puma and 15 from Eternal. Each tire she logs, and here is the distance. Okay, so this is going to take a few minutes. I'm going to let you put these into list 1 and list 2. I will be back in just a minute. That'll take you a few minutes to do anyway, because I have to do it also. So I'll be right back. All right. So I have 13 in the first list and I have 15 in the second list. So that's one way to check that I have all the data in there. So if I'm missing one, then I need to go through and find it. The order doesn't matter. So if you did miss one, you can just tack it on at the bottom. Doesn't matter. Also, I'm noticing that all of them are 2 digits and possibly with a decimal after it. And so I don't see any 3 or 4 digit numbers here. So that's another way that there's a good chance that I didn't mess this up. And I still could have. Okay. It says, assume that the two populations of distances driven are approximately normally distributed. Can Lashonda conclude at the 1% level that there is a difference between the population distance means when they need to be replaced? They mention nothing about population standard deviations. So this is going to be a 2 sample t-test. So this is definitely t. Degrees of freedom, if you remember, it's the smaller of the 2 minus 1. So my degrees of freedom in this case is going to be the 13 minus 1, which is 12. All right, so I need to do inverse t. And again, this is a 2 sample t-test. And we have raw data. We're not pooling. So our test statistic is 3.310. And our p-value is 0.004, which is clearly less than our alpha. And I'd like to point out that I am definitely in rejection zone. Which means we're going to reject the null hypothesis, meaning that there is a difference in the mean. We are almost done. Hay preguntas, any questions?
I have a question.
Yep.
I know this is a sample t-test, two sample t-test.
Correct.
How can you tell if it's an interval? Are you getting to that?
No, it would need to say find a confidence interval.
Okay, got it.
Yep. All right. If I'm not mistaken, we have one more to go. Number 17, we're not doing. I took it off of your practice test. It's gone. Which brings us to our dependent. A computer manufacturer is interested in comparing assembly times for two keyboard assembly processes. Assembly times can vary considerably from worker to worker, and the company decides to eliminate this effect by selecting 10 workers at random and timing each worker on each assembly process. Half the workers are chosen in process 1, the rest are on process 2. And we have the results here. And what we are going to be interested in only are the differences. That is all we care about. So that is going to go into list 1. You can put it in whatever list you want, actually.
What section was this again?
This one is section, let's say 9.3.
Okay. Thank you.
Yeah, I'm a little sketchy on that one. I think it's 9.3. It's the one titled dependent.
Okay.
All right. Based on these data, can the company conclude at the 5% level that the mean assembly times for the two processes differ? So if you remember, we start here. They want to know if there's a difference or not. All right, so this is just going to be a straight up t-test.
Is that MD?
Yeah, it's supposed to be a subscript, like a lower, smaller subscript.
Okay.
Yep.
And we would put that in ALEKS.
Yes,
Okay. I don't remember that part. Sorry.
that's all right. All right, so let's set up a T. Ooh, that was bad. A little better, not much. And this is a two-tail. And what's our alpha? So this 0.025, 0.025. So we need inverse T. N is 10. Degrees of freedom is 9. So inverse T, pardon me. All right, we've already found the critical values. So now we need the test statistic and the p-value. Again, this is just a straight up t-test. Oh, this is data. All right, and our p-value is definitely bigger than our alpha. So and I'll notice that my test statistic is definitely not in the rejection region. And my p-value is bigger than my alpha. So can we conclude that the processes differ? Nope, we cannot. Because we're keeping the null hypothesis, no difference.